The power formula in integration has been categorized into two, one of which was discussed previously. This video will be discussing the general power formula. Welcome to Integral Calculus. What is the difference of the general power formula from the simple power formula? The simple power formula has the equation in terms of x, which is considered as an individual variable. Some examples of which are the variable t, or 5z, or even w over 2. These are all in just one term defined by the variable. The general power formula, on the other hand, still uses the same equation but has u instead of x, where u is used to denote a single term, not just a variable. For example, use the binomial t plus 1 or another binomial 5z squared plus 4z, or even the polynomial half of the quantity w squared less 2w plus 1. The general power formula is more likely to undergo distribution of the integrand as it has more terms for u. The following are examples of integration using the general power formula. Say we are to integrate the quantity z plus 3 raised to 4. First is to identify the term. Is it in the pattern of x raised to n, which means is it in a single variable, or perhaps it falls under u raised to n. Since the power of 4 considers the whole binomial as a single unit, we use u raised to n, where u is the binomial z plus 3, and its derivative is just the derivative of z, and then n is taken as 4. So by using the general power formula, we get the quantity of z plus 3 raised to 4 plus 1, and everything is over 4 plus 1. Then add c. The integral can be simplified as the quantity of z plus 3 raised to 5 over 5 plus c. The second example looks for the antiderivative of dx over the quantity of x less 5 squared. With a denominator, adjust the formula first in a one-liner function before applying any integration procedure. So place the denominator up by taking its negative exponent, making the function x minus 5 raised to negative 2 times dx. Then again, check if the variable is single or in a group. It is the latter, so we consider it u raised to n, where u is x minus 5, giving du as dx, and n is negative 2. After identifying the parameters, use the general power formula to come up with the quantity of x minus 5 raised to negative 2 plus 1 over negative 2 plus 1, and then add c. This is simplified as x minus 5 raised to negative 1 all upon negative 1 plus c. And to keep a positive exponent, place the final integration as negative 1 over x minus 5 plus c. The next example has the integral of the square of 4x plus 1 times dx. Take the unit which is squared and identify if this is x raised to n or u raised to n. Having a group of terms which is raised to 2, this term is u raised to n, where u then is taken as 4x plus 1 and its derivative is 4 dx. N is also equal to 2. Since the derivative requires 4 dx, we have to incorporate 4 into the equation, but then also have to multiply everything with 1/4, so as not to alter it. Then we can proceed to the power formula, which turns out as a quarter of the quantity 4x plus 1 raised to 2 plus 1 all over 2 plus 1 plus c, simplified as 1/4 of the quantity 4x plus 1 cubed over 3 plus c, and further reduced as 1/12 of the cube of 4x plus 1 plus c. The next problem progresses with its difficulty, giving y dy over the root of a squared minus y squared. Again, the occurrence of the denominator needs a little adjustment before integration. So place the root up and have a squared minus y squared raised to negative 1/2 times y dy. The term is then tested if it falls under simple or general power formula. And again, it is a u raised to n, where u is the square of a less y squared, and its derivative is taken as negative 2y dy. Also, n is negative 1/2. Adjust the function to have the proper derivative and multiply negative 2 with dy. Then, place negative 1/2 right before the integrand. With the function already adjusted, integrate it through general power formula and get negative half of a squared minus y squared raised to negative 1/2 plus 1, all over negative 1/2 plus 1. Then add c. This is simplified as negative half of the quantity a squared minus y squared raised to 1/2 over 1/2 plus c, where 1/2 cancels out, bringing about the negative of a squared minus y squared raised to 1/2 plus c. Moving on to example number 5, where it requires the integral of the cube of the quantity 1 minus x squared dx. Having the cube of a binomial can make us decide that the term falls under u raised to n. So take u as 1 minus x squared, and its du comes out as negative 2x dx. N is also 3. Go back to the derivative of negative 2x dx. We can incorporate negative 2 into the function, but we are still lacking an x. This tells us that taking the binomial as a unit is not a wise idea. So, the other method is to expand the binomial to take out the cube, using Pascal's triangle. We can identify the coefficients for expansion as 1, 3, 3, and 1. So expand the cube of 1 minus x squared as 1 cubed plus 3 of 1 squared times negative x squared plus 3 times 1 times negative x squared plus the cube of negative x squared. And this is reduced to 1 minus 3x squared plus 3x raised to 4 minus x raised to 6. Continue with the distribution of the integrand among the terms and get 4 simple integrations. The first term doesn't have any simplification, but we need to check requirements starting at the second term. X squared dx falls under x raised to n, where x is x, dx is dx, and n is 2. The third term has x raised to 4 dx, which also is under x raised to n, with x as x, dx as dx, and n as 4. Lastly, x raised to 6 also falls under x raised to n, where x is x, dx is still dx, and n is 6. Use the simple power formula to have x less x raised to 2 plus 1 all over 2 plus 1, then add 3 with x raised to 4 plus 1 over 4 plus 1, then subtract x raised to 6 plus 1 over 6 plus 1, and then c. So the final integral is x minus x cubed plus 3/5 of x raised to 5 minus x raised to 7 over 7 plus c. Example 6 requires the antiderivative of the product of x squared with the square of the quantity of x squared plus a squared with dx. Having a one-liner function, let's test the integration variable, which is seemingly an u raised to n, where u is the square of x plus the square of a and its derivative is 2x dx. N is 2. Du is 2x dx, but what is available is x squared dx. So, we got an excess x, showing that the general power formula is not applicable. Thus, the next option is to work on its using simple power formula, and that is done by first expanding the function using Pascal's triangle. Taking the square of x squared plus a squared is the square of x squared plus twice of x squared times a squared plus the square of a squared. The expansion is then taken as x raised to 4 plus 2a squared x squared plus a raised to 4. Place the expansion into the function. The next step is to distribute the factored x squared and the integrand among the terms, giving the integral of x raised to 6 plus 2a squared times the integral of x raised to 4 plus a raised to 4 times the integral of x squared. The first term has an x raised to n configuration, where x is x, dx is dx, and n is 6. The second term is also an x raised to n, with x as x, dx also as dx, and n as 4. Then the last term considers x raised to n as well, where x is x, dx is dx, and n is 2. Integrate all terms to have x raised to 6 plus 1 over 6 plus 1 plus 2a squared times x raised to 4 plus 1 over 4 plus 1 and a raised to 4 times x raised to 2 plus 1 over 2 plus 1 and then c. This is simplified as x raised to 7 over 7 plus 2a squared times x raised to 5 over 5 plus a raised to 4 with x cubed over 3 plus c, which can be written as x raised to 7 over 7 plus 2/5 of a squared x raised to 5 plus a third of a raised to 4 x cubed plus c. Another example involves the integral of x squared minus a squared over x squared. And again, since there is a denominator, we try to place it up and test the whole function if we are to use simple or general power formula. Seemingly, we have a u raised to n, where u is x squared minus a squared, and its du is 2x dx. But check the expression, and what we got is x raised to 2 dx, which does not conform with du, as there is an excess of x. So we separate variables by going back to the original function and divide each numerator by x squared, resulting to the integral of 1 minus a squared over x squared dx. Separate integrands and have the integral of dx less a squared times the integral of dx over x raised to 2, which can be written as the integral of x raised to negative 2 dx, to avoid having a denominator. From here, check the variable and it is now simply x raised to n, where x is x, dx is dx, and n is negative 2. Now, integrate the function with simple power formula to have x less a squared times x raised to negative 2 plus 1 over negative 2 plus 1. This is simplified as x less a squared times x raised to negative 1 over negative 1, which can be written as x plus a squared over x.